Let's talk about simple, elegant mechanisms. Those clever inventions that make you smile when you see them work. Today, we're diving into the pantograph, a deceptively simple linkage that's shaped our world for centuries. Before scanners or CAD, how did people copy and scale drawings? With a physical tool, a set of hinged bars that could trace and draw at the same time. This humble device was the backbone of drafting and design, and its principle is still at work today, often hidden in plain sight. That zigzagging arm on top of electric trains, that's a pantograph, a direct descendant of the tool used by 17th century mapmakers. We'll explore how this core mechanical concept evolved from a draftsman's aid to a critical part of modern infrastructure. By the end, you'll spot pantographs everywhere and appreciate the elegance of their design. So, what is a pantograph? At its core, it's a mechanical linkage of four bars connected to form a parallelogram. One corner is anchored, while two other points serve as the tracer and the drawing point. As you move the tracer along an image, the drawing point mimics the motion, creating a copy. The real magic is in scaling. By adjusting where you attach the tracer and drawing points, you control the size of the copy. Architects could scale up a sketch, or surveyors could shrink down a map, all with this analog scaling machine. Think of it as a mechanical amplifier or reducer for motion. The parallelogram's geometry locks in a predictable, repeatable relationship between the original and the copy. No guesswork, just reliable, accurate results. In a world before digital tools, the pantograph was a guarantee of precision. It's a perfect example of simple rules creating powerful results. Step back to a time before computers, when draftsmen ruled and the pantograph was their secret weapon. Technical drawings were painstakingly created and scaled by hand. One mistake could be costly. Instead of endless measuring, engineers used the pantograph to trace a small drawing and produce a full-size template with perfect accuracy. It worked in reverse too. Surveyors could shrink large maps for reports, preserving every detail. This tool bridged the gap between fieldwork and office, fostering a deep, hands-on understanding of mechanics and geometry. Using a pantograph, draftsmen felt the relationship between original and copy, learning about linkages, pivots, and geometric similarity. It was more than a copier. It was a teacher, demonstrating engineering principles with every line. In today's digital world, that tactile education is often lost. The pantograph was a masterclass in motion, right at your fingertips. Think the pantograph is obsolete? Think again. It's still hard at work. On electric trains, that diamond-shaped arm on the roof is a heavy-duty pantograph, keeping steady contact with overhead power lines as the train moves. Its parallelogram linkage allows smooth vertical movement, ensuring a reliable electrical connection at high speeds and in all weather. In manufacturing, pantograph-based machines let operators trace a template, while a cutting tool replicates the motion, producing identical parts without complex programming. Even in robotics, parallel linkages inspired by the pantograph keep robotic arms level and precise. The next time you see a robot or a train, look for that familiar geometry. The pantograph's principle, replicating and scaling motion, remains indispensable. From delicate drawings to high-voltage railways, its legacy endures. A 400-year-old idea, still powering the modern world. How does the pantograph actually work? It's all about the moving parallelogram. Four bars, joined at pivots, form a shape that always remains a parallelogram as it moves. Fix one point, the anchor, and designate the tracer and drawing points. As you move the tracer, the drawing point follows, always in a straight line with the anchor. The secret is similar triangles. The distance from anchor to drawing point is always a fixed multiple of the distance from anchor to tracer. That ratio is your scaling factor. Double the distance, double the size, halve it, and you shrink the copy. Adjust the pivot points, and you change the scaling ratio. Every movement is perfectly scaled thanks to unbreakable geometric laws. No batteries, no software, just pure, visible math in motion. That's the brilliance of the pantograph. When engineers design a pantograph, they use a special language, the engineering drawing. Instead of realistic pictures, they use simple lines for the bars and circles for the pivots. The anchor is marked clearly, and tracer and drawing points are labeled, often as T and D. The drawing specifies the scaling ratio, either directly or through dimensions. This schematic approach strips away the fluff, focusing on function over form. It's fundamental to kinematics, analyzing motion, calculating forces, and understanding how the mechanism works. By reducing the pantograph to lines and circles, engineers can predict its movement and performance. These minimalist diagrams contain everything needed to build or analyze the mechanism's elegant dance. In a world of 3D printers and robots, why care about a centuries-old tool? The pantograph is a perfect introduction to linkages, the bones of every moving machine. Building or sketching one gives you a hands-on grasp of motion, pivots, and scaling. This knowledge is the foundation for modern robotics and automation. A robotic arm is just a complex series of linkages. Understanding the pantograph is step one. The principles of motion transfer and geometric constraints are timeless. The pantograph reminds us that innovation often comes from mastering fundamentals and applying them in new ways. By appreciating these elegant mechanisms, we connect the past to the future and become better problem solvers.